Okay, welcome back one last time, everybody. How's everyone feeling? Oh, okay. It's the last session of a long 2 days, I know. But this is going to be a very special session. I'm personally looking forward to it immensely. It's going to be very, very interesting, I think, for all of you. Because as I said, we're moving from big data, talking about how we build our data infrastructure, to big code, talking about our developer infrastructure. What is it like to be an engineer at Facebook? How do we store our code? How do we write our code? How do we push it to production? And again, some of this will blow your brains, so I hope you enjoy yourselves, and we're going to kick off with Brian O'Sullivan.
All right, thank you, James. So I want to roll the clock back about 10 years to when Facebook was a very small, spunky startup. Back in the day, we used to use a revision control tool called Subversion to get our code onto our machines so that we could actually do our jobs. And the way that we did releases was very much the kind of thing that you can get away with when you're essentially based out of a garage. We would copy Facebook onto the server that was responsible for Harvard and kind of poke at it a little bit, see if it was still working. If it worked, great, let's copy it all to all the other Ivy League machines and go along from there. Every day, 10 a.m., this was the process. Now, not surprisingly, things have moved on a little bit from then, right? We now have over 1 billion people that we need to serve. We have thousands of developers working for the company. And we now have 3 major platforms: iOS, Android, and of course, the web. Nevertheless, as everything has grown by orders of magnitude, we have continued to push our code very frequently. We continue to develop our code at a very high rate, and making this work well across 3 diverse platforms has meant putting some of our best engineers to work on the challenges of tooling and process. So let's talk a little bit about some of the work that's been involved here. One of the first things that we've had to do as we developed on Android was focus on very, very fast builds, which we produced a tool called Buck to do. Buck not only works for Android now, we also use Buck for developing on iOS. And do we have any iOS developers in the room? Anybody who's familiar with trying to merge conflicts across Xcode project files should be delighted by the idea that they can use a different build tool that still works with Xcode. That's where we are with Buck today, and it's made a great difference to our ability to move fast and refactor a very large iOS application. Meanwhile, for web development and for React development, we have the hack and flow type systems for PHP and JavaScript that make a huge difference to our ability to manage the correctness of a large code base without sacrificing on a very fast turnaround time. And of course, also on the good API front, we need to be able to develop applications quickly that are easy for our engineers to work on, and hence React and React Native, which we've heard a lot about today. So the goal behind all of these things is that we don't want our engineers working and waiting on computers and sitting there wondering what's going to happen next. Instead, we want the computers working as fast as possible so that our engineers can be in a state of flow as they work. So let's talk a little bit about what the daily life of a Facebook engineer actually looks like. What's their experience of creating code, getting it into production? So let's start with getting code into the hands of an engineer to begin with. So back in 2005, you'll recall that I mentioned we were using Subversion. In 2007, we moved over to a tool called Git, which I'm sure needs no introduction for people in the room here. We used a bridge so that we could continue to have our Subversion infrastructure in place while moving over to Git for people that needed to. This gave us a great improvement in flexibility of workflow. It gave us a decentralized way of working that was safer. You could switch between different tasks. All of the benefits that everybody in the room is familiar with, we enjoyed, and it was great. As time went by, we added new platforms. We had specialized server-side code. Some of the projects that you've heard about in this room today are developed in a repository that we call FB code, which is all server-side code that is mostly C++, Python, Java, that sort of stuff. We also, of course, introduced iOS and Android, And as we developed these, there was no need to share code between these wildly divergent platforms. We were just learning Android because it didn't exist before. We were just learning iOS because that didn't exist before. There was nothing in common between these three different spaces, so they naturally arose as three different Git repositories. Now, of course, time went by, and our need to share across these different platforms began to increase. We needed to be able to share things like artwork, and of course, code as time went by. So the world that we have today is we've got three different silos for our work to live in. Supposing somebody develops some work on, say, the Android platform, and they want to make that work available to engineers who are working on iOS. What do they do today? They have to make a copy from Android over to iOS. And you can kind of see where this is probably going to lead, right? Naturally enough, that kind of code also is going to end up getting copied over to the server side. And now we've got several different sets of people, all of whom are trying to figure out who actually owns the master version of this piece of code or of this art asset or whatever it happens to be. This leads to global unhappiness, right? If you find a bug on one platform, can you be sure you're actually fixing it everywhere? So this is not a good place. It's an adequate place, but it's not all the way good, and it slows us down, it introduces confusion. So where we want to get to is a project that we're on the verge of rolling out, where we have a single repository, which we're calling FB Source, and we're just weeks away from having this actually shipped to our engineers. The purpose behind FB Source is to maintain the flexibility that Git provides us with, while also giving us performance across a much, much larger code base and much, much larger repository. So we are moving all of our code to a single repository. This is something that I believe a few other companies have done that you may have heard of, but it's very exciting for us to be in this same place now. The purpose behind FB Source is not some bureaucratic exercise. It's to make life easier for our engineers. We want it to be easier to share code across platforms. We want it to be easier to contribute code that works across all of our platforms. We also are in the habit of making large-scale changes that affect all of the code that we write. We want to make that a safer and more straightforward process, and we want it to be possible for engineers to have just one set of tooling, uniform tooling, that works on every single platform that they're familiar with. So if you were to take a look at a Facebook engineer's experience of working with Git today, it's quite slow. There's a large number of files in the repository. There is a deep amount of history because of the number of people who've been working on this platform over the past half-decade of its existence. And both of these things contribute to a large footprint, and a large footprint makes Git slow to deal with. So let me give you some numbers associated with that. The humans at Facebook, this is not even automated systems, the people who actually work with our source control tools as part of their jobs run over 1 million source control commands every single day of the week. They issue over 100,000 commits every single week, right? This stuff has to be fast. If somebody gets distracted, they're going to lose concentration, they're going to flip over to something else, and they're going to suddenly slow down vastly. So we're in the process of switching from Git to a very similar tool called Mercurial. We've made some major architectural and performance-related improvements to Mercurial so that it performs better than Git for this much larger repository that we now have. The first of these is called sparse checkouts. Sparse checkouts is an interesting feature because it allows you to, even though you have a conceptually much larger space that you're working on, check out and work on only the files that you're actually caring about. The build system also knows how to check out more files so that if you happen to not have exactly the ones that you need, they get transparently pulled onto your machine for you. So this greatly reduces the surface area of data that's on your machine that you need to pay attention to. On top of that, we've also made it possible to work without all of the history needing to be on your machine. The purpose behind this is to make sure that the minimal amount of information that's necessary is available at your fingertips and isn't causing performance problems with your machine, but any extra history that needs to be downloaded is done so automatically and transparently so that there's no visible difference in experience for you as an engineer. So some of the changes that we've made to Mercurial have made it up to 50 times faster than Git for the kinds of common operations that our engineers perform every day. We have made over 2,000 improvements to the open source version of Mercurial, and I'm proud to say that we do all of our work in the open so that the engineers who do this work share that with other organizations like Mozilla and our friends down the street at Google who are using this stuff at scale. So this is exciting not just to us, but also to other people who want to be able to use distributed revision control tools in a large environment. So let me talk a little bit about one of the just detail-oriented aspects of getting this stuff to work well. If you've used a distributed revision control tool like Git in a team of a few people, you'll be familiar with the idea that if you want to push your changes to a remote repository and somebody else has pushed changes more recently than you, you need to pull down their changes, then push your changes back. Now, as you might imagine, this is a natural bottleneck, and if you have hundreds or perhaps thousands of engineers all racing in this way, everybody pulling, rebasing, pushing as frantically as they can, you end up in a situation where people are doing needless make work, right? How can this possibly make sense to then increase by a factor of 3 when we're unifying these 3 different platforms, the number of possible points where you can have these rebase, pull, push conflicts? Well, what we've done is we've moved the work over to the server side of doing the rebases, and we've also benchmarked this automatic server-side rebasing so that we can say with confidence that at the end of the year, when all of this actually has hit and our engineers are depending on it for their day-to-day work, we'll have 3 times the capacity necessary to handle this workflow. Nobody will ever have to find themselves in the situation of pulling, rebasing, and pushing. It all just will naturally flow for them. So that's just one of the small details that has to go into making this kind of workflow work well for a very large, fast-moving company. So let me reiterate some of the things that we've done here. We're moving to a much bigger distributed repository than I'm aware of has been used elsewhere. We're simultaneously making this a better work experience for our engineers, faster and with a smaller footprint, and we're doing all of this work in the open so that people out there who would care to use it can do so freely and easily. And once again, the purpose behind putting our best engineers to work on this is that we don't want our engineers waiting on their machinery. We want the machinery serving the engineers themselves. So that's the process of getting bits from a server onto your local machine. Obviously, the next part of your daily experience as a Facebook engineer is actually doing the work itself. And I'd like to introduce Christian Lignito, who is a manager on our release engineering team, who'll talk some about that. Thank you, Christian.
Thank you, Brian. So Brian talked about how you get code onto your laptop as an engineer at Facebook. And I'm going to talk about writing code locally. Again, my name is Christian Lignito. I work on release engineering, and this is my mugshot. After you get the code on your laptop, the next obvious step is to actually write new code. And the first thing a developer does, regardless of platform, is open their code editor. Naturally, this is VI, because it's the one true editor. Right? Yeah? Great. All right. Or maybe Emacs. I don't really want to get into that debate. It turns out, at Facebook, engineers like to use a lot of editors. Sometimes this is because of familiarity. They've used the same thing for a long time. They want to keep on using it. But often, developers trade off between IDE-type features and speed. IDEs have fancy stuff like autocomplete, click-to-symbol, source control integration, but they need to do work to provide those features. For instance, maybe indexing the code in the repository. This work often slows IDEs down compared to simple text editors. This is especially true at Facebook. As Brian mentioned, we have large repositories with lots of apps written in many programming languages. Loading them up in IDEs is pretty painful. For example, let's talk about Xcode. We are hearing reports from product engineers that developing in Xcode at Facebook was an exercise in frustration. So we measured, and it turns out it takes, on average, 3.5 minutes for a developer to start up Xcode and load Facebook for iOS, plus its dependencies and its test. That is not great, and that's 3.5 minutes that a developer is not writing code. But maybe you only start Xcode once a day or once a week. You go home at night, you sleep your laptop, you come to the office, you reopen your laptop. Every time you open Xcode, you still have to go through indexing. And for our developers at Facebook, on average, it takes 5 minutes for Xcode to index Facebook for iOS. And while it's doing this, it's pegging their CPU and making their IDE less responsive. But finally, you get past all those, you go to write your code, you're writing it, it's the great next thing, and what happens? Xcode crashes. Across our iOS developers at Facebook, Xcode crashes on average 50 times every day. Now, that's not an individual sees 50 Xcode crashes a day across all of our iOS developers. I want to note, these metrics we all measure. So when a developer comes and says, my IDE is not responsive, or my builds are slow, or pulling down from Mercurial is slow, we can see, are they an outlier? Are we getting better or worse over time? So I highly suggest you do metrics for your developer tools as well. Now, I don't want to pick on Xcode. Pretty much every IDE has this sort of issues at Facebook. It's not inherent in the IDEs we use, it is inherent in the way Facebook does development. But as Brian mentioned, the way Facebook does development is very valuable, and we don't want to give that up. At the same time, we don't want humans waiting on computers. We want computers waiting on humans. One way we could accomplish this is to give up those IDE features. Turn off autocomplete, turn off source control integration, maybe not use IDEs altogether. But we at Facebook don't like that. We think IDEs are useful and make us more productive. We want to have our cake and eat it too. So we looked at how to do that, and it was hard determining where to even start. At Facebook, we have many platforms, and across those platforms, our engineers use many different editors. There was no clear one editor to focus on, and we couldn't support them all. At the same time, this thing called React Native happened. You might have heard of it. And React Native sort of broke the mold. Previously, you worked on an iOS app, you worked in Objective-C or Swift, and your tools like Xcode understood that. But React Native has web tech as well as native mobile bits. It spans multiple stacks. And none of the IDEs we are currently using provide a great experience. They're made for a particular technology or a platform silo. So what does the React Native developer experience look like today? First, you launch Terminal because you want to start up Node.js because you want that rapid iteration cycle that JavaScript gives you that React Native is so great at. But you also need to launch Xcode because there are native components of React Native, and Xcode knows how to build and push to a phone, for instance. But Xcode doesn't know a ton about JavaScript. So chances are you launch an editor that does. And then finally, once you write your code, you need to actually debug it. Chrome has really good JavaScript debugging tools, so you open up the Chrome DevTools as well. This means to develop a React Native app today, you need to have 4 apps open with 4 windows, and none of them talk to each other. And you, as a developer, need to context switch depending on what you're doing at this point in time. At Facebook, we think React Native is the future of mobile development, and this development experience is not acceptable. So we want IDE features, we want them to be fast, and we want to support something like React Native that spans multiple stacks. And again, we looked at all the IDEs we were already using, and nothing really fit the bill. So in true Facebook fashion, we built our own. We built our own IDE, and we call it Nuclide. And this is the logo. And this is what it looks like. Pretty standard IDE stuff. Now, I lied a little bit when I said we built our own IDE. We ended up not building it from scratch. Nuclide is based on Atom, GitHub's open source editor. In fact, Nuclide itself is implemented as a set of plugins for Atom. We are not forking Atom. We're working closely with GitHub and contributing as much as possible back upstream. Why did we base Nuclide, Facebook's IDE, on Atom? First, it's high quality. At Facebook, we don't force engineers to use a particular editor or IDE, so the quality needs to be there because the engineer needs to opt in and think it's going to make them more productive. Second, Atom's hackable from the start, and at Facebook, we obviously love hacking our own tools. Third, it's built with web technology. We have lots of people at Facebook that know how to edit JavaScript, React, CSS, and right away they can dig into the IDE and add their pet feature. And finally, Atom has an active community. The community is providing these plugins like VI bindings, Emacs bindings, syntax highlighting, and that means us as an internal team at Facebook doesn't need to do that. It means we can focus on Facebook-specific problems, as well as filling in the gaps where the community hasn't yet provided a solution, and of course, contribute it back. Now, I'm going to get to a demo, but I want to make it clear what Nuclide is not. Nuclide is not a generic Xcode replacement. We're not trying to replace Xcode. Xcode is good at what it does. In fact, Nuclide does not even read Xcode projects. Nuclide talks to Buck, our open source build tool that tells it what and how to build. Nuclide is not a way to build iOS apps for other platforms. It doesn't give you anything above and beyond Xcode in that regard. And part of the reason why is Nuclide uses the same tools Xcode does under the covers, Clang, LDB, all that sort of stuff, to do its work. All right, let's switch over to the laptop. Let's give you a real demo of this. Enough talk. Hopefully all of you have the F8 app on your phone. I'm going to be editing the iOS F8 app. So again, starting Atom, and it'll start up here. And this is Nuclide. And you can see this is some Objective-C code. For the F8 app. Now let's go down here, and let's change the text on the status bar to be a different color. And as I start typing, Nuclide has in the background went out and talked to Clang. Clang has tried to compile your code and has said, hey, I have a syntax error, just like Xcode. So we're not giving up those features to use Nuclide. Now I start typing, and I get autocomplete, right in line from Clang with types, just like Xcode. So now I'm going to do this, and I get tokens, just like Xcode. I can tab to each thing I need to fill out. And let's do this translucent, and I have a message here. And it tells me this is deprecated, I need to do something else, right in line. Let's make this default. Let's make it not animated, and save it. Now let's build it. Select our target, press build. Now we got to wait a little bit. Right? You'll notice this panel on the bottom has come up to show us the build, just like you would expect from a normal iOS development tool. Now, while this is happening, I want to point out some other features. You can notice that the tree on the side has a different color. That's because I just saved this file and edited it. It went to the Mercurial underneath it, saw that I edited, and marked it in the UI. Sorry. Obviously, GitHub is focused on Git. Atom previously did not support Mercurial. We had to add that in, and we're going to contribute that back to the community. All right, while this is compiling, I'll show you another feature. In Xcode, you can hold Command and hover over any symbol and click to where the symbol is defined, whether it's in your code or in headers. It's really useful to go, hey, where did this come from? So I'm going to hover over UI user notification type alert and click. And it has loaded Apple's headers for iOS and points me right where it is defined in their headers, and I can see that value. OK, it looks like our build has succeeded. Let's choose our simulator device. Let's keep it iPhone 6, and we'll press run. And there is the F8 app. We just edited Objective-C with autocomplete, compiled, installed in the simulator, all without using Xcode. Now, I really like this swooshy thing. I don't really know what it's called, but it's kind of hard to see. So let's edit that. It turns out this app is a React Native app. And that swooshy thing, technical term, is created by JavaScript. So let's open that up. So this is the JavaScript for F8 animating curve view. And let's scroll down to where that's actually made in React. We see stroke width, we see a stroke style, and I don't really like hard coding that stuff in the component. Let's make some variables. And we'll copy that from there. And let's replace those values in line. And you'll see, even though we're editing JavaScript, we get types and autocomplete from Flow. Let's save that. And again, I wanted to make this a little easier to see, so let's make it solid red. And thick. Now we save it. We go back to our simulator where our app is already running and already compiled. Let's cold start it, and let's reload it somewhere. There we go. So there you go. We live edited JavaScript with React Native. We had edited Objective-C, compiled, installed it on the simulator, switched to JavaScript, got all those nice click-to-symbol autocomplete, managed to edit and refresh without having to compile, all within one editor. Back to my slides, please. But at Facebook, we don't just do mobile. Of course, I showed iOS, showed some Flow. At Facebook, we have most of our front end written in Hack, which is a typed PHP, basically. And in the past, we have said we're going to create a Hack IDE. And it doesn't make much sense for us to be investing all this time and effort in Nuclide for mobile and React Native JavaScript and to create another IDE for Hack. So I'm pleased to say that Nuclide is the one IDE that Facebook is using for iOS, Flow, JavaScript, and Hack on the server side. Now, obviously, server-side code is different than mobile code, so there's a couple other features that we want to cover. So if we can go back to demo, let's check them out. In the same view, I'm going to connect to a remote server. And let's connect. What I'm going to connect to is this project that's available on GitHub. It's the Hack example site. And it looks like this. So this is running on a remote server, and I'm running Nuclide locally. Let's switch back, see if we've connected. The Wi-Fi is a little not great right now. Cool. So we've connected. So we have this folder up here with the F8 app locally on my laptop. And below it, we have this folder that's actually on a remote server, and we have the files for the Hack example site. So let's change this text here. We will load it, and Nuclide transparently goes to the server, grabs it, pull it back. We'll save it, and again, Nuclide saves it locally, sends it to the server transparently. And if we reload this, we'll see that. That's really great. But that Hack cookbook was there twice. We should probably put it in a variable. So let's make a variable. And as I'm typing, you can see that Nuclide is talking to hack on your remote server and is type checking and compiling just like Clang or just like Flow was. So I get that immediate feedback if I have a syntax error or not. OK, let's make our title use this. And again, we get autocomplete just as we did with Objective-C code, just as we did with JavaScript code, all in one IDE. Oops. User-defined types, and we can call that function when created. So let's save it and go back and check it out. And there you go. Thank you. Back to the slides. We created Nuclide to solve problems that Facebook is hitting across the technologies we use. But we think Nuclide is going to be useful for all of you as well, especially if you're a React Native developer. In the coming months, we're going to provide public access to this. We're going to ship it publicly and open source as much as we can. If you're interested, go to nuclide.io to learn more about it, and you can sign up for an announcement when we're ready to ship it. So I've talked a little bit about what happens and how you edit code, hopefully in Nuclide, at Facebook. Katie is going to come up and talk about what happens after you send your code to our continuous integration system. Thank you.
Thank you, Kristen. I'm going to be talking about continuous integration at Facebook. This is a system that builds and tests all changes to the Facebook codebase made by Facebook developers. And our #1 goal with continuous integration at Facebook is developer efficiency. We do not want our developers waiting on computers to build and test their diffs. We want computers to be waiting on our developers to write more diffs. So to make that possible, we have 3 key goals for continuous integration at Facebook. First, the system must provide high-signal feedback to developers. We do not want developers chasing down failures that are not their fault, because that's a waste of developer time. Second, the system must provide rapid feedback to developers, because our developers will not wait for it. Moving fast is a really important part of Facebook's culture. Finally, the system has to provide frequent feedback to developers, because the sooner that we let them know about a problem with their diff, the faster and the easier it is for them to fix it. And of course, to do all of this at Facebook, the system has to operate at scale. So to give you a feel for how we provide high-signal, rapid, and frequent feedback to developers while operating at Facebook scale, I'm going to tell you about Sandcastle. Sandcastle is the name of the continuous integration system that we use at Facebook. And to give you a feel for where it fits into context, I'm going to take you through the life cycle of a diff at Facebook. Now, a diff is analogous to a pull request in the open source world. So I'm a developer at Facebook. I want to change the code. Here's that code, how that code is going to get from my fingertips to your phone in the course of about 1 to 2 weeks. This all starts, of course, with local development. And as you heard about from Christian, I will, of course, be using Nuclide for my local development. And it's important to note that this process of testing and getting feedback on my diff has already started right here on my laptop. It's really important at Facebook that I will never, as a developer, write code and then toss it over the fence for somebody else to write tests for it. It is my job as a developer at Facebook to write tests for my code, and my reviewers will make sure that I do. So I've written my code, I've written tests for it, I'm ready to put it up for review. This is when I'll go to create a diff. You can see a picture of a diff at the top here. As I said, a diff is analogous to a pull request. This is a proposed change to the code base. So after I hit enter and submit my diff, if one of my coworkers goes and pulls down trunk, they will not get my change, not yet. Now we're going to run some tests on my diff right now on my local laptop. And we're going to run tests at many more points throughout this process. And the number and the scope of the tests that we run is going to grow as the diff gets further from my fingertips and closer to your phone. And there are 3 factors that we use to decide which tests to run at each step. First is coverage. We're not going to run the test unless your diff might actually have broken it. The second is flakiness. If a test has a history of being flaky, then we're less likely to run it. And finally, speed. The faster a test runs, the more earlier in the process and the more frequently we're willing to run it. So right here on my laptop, before the diff ever goes up for review, it has to pass a very small set of very high signal, very fast tests. So let's say my diff passes them all. And now I hit enter, and my diff goes up for review. This is when the diff is going to leave my laptop. And this is great for me as a developer, because it means I can go do something else. I can go write my next diff. This is where Sandcastle takes over. Now, Sandcastle is similar in principle to Travis. How many folks here use Travis, or have heard of Travis at least? OK, good number of you. It's similar to Travis, Jenkins, BuildBot. It's our continuous integration system, and it runs in the data centers at Facebook. And this is really important, because this gets us massive parallelism. And we need that massive parallelism, because our goal, our team's goal, is to get as much feedback to developers as we possibly can within 10 minutes of when they submit that diff. Now, we can't always do this as well as we'd like, but this is what we're always shooting for. In particular, we found that at this stage, if we run fewer tests, but we get feedback to developers more quickly, then they're actually less likely to break things than if we run more tests, but take longer to get them feedback. In addition, we want the reviewers to have the results of the tests available to them as soon as they go to review the diff. So we want to get as much feedback as we can in 10 minutes. So given our parallelism in the data center, we're going to run my diff on a variety of different apps and in a variety of different configurations. Again, we'll use coverage to limit which ones we do to those that are needed. And we're also going to expand the scope of the tests that we run. Now, the vast majority of the tests at Facebook are unit tests. They test one component and one component only, a PHP class, for example. We've got a smaller set of integration tests that test the interaction between multiple components, but they still mock out things like the database. And finally, we've got a smaller set of end-to-end tests that test the entire workflow as a user would. For all of our end-to-end tests at Facebook, we use WebDriver. WebDriver is an open source JSON wire protocol. I encourage you all to check it out if you haven't already. And one of the great advantages of WebDriver is that it's got applications across many different platforms. So if I'm writing an end-to-end test for Android, for iOS, for the web, the APIs that I'm going to use are going to look just the same. So this is great not only for keeping our developers efficient, but also for making them really flexible and working across platforms. So Sandcastle is going to run all of these different types of tests on my diff, give me feedback about them. It's also going to have a performance analysis and a size analysis, so I'll know if I've regressed key performance metrics or if I've notably increased the size of an app, for example. And you may have heard earlier in the day today, there's a team that's been working hard on performance analysis. They're designing racks so that we can eventually have iPhone and Android devices in the data center so that we can really scale these performance testing efforts. So we try to get all of these different types of feedback on the diff as much as we can within 10 minutes. Let's say my diff passes all of those tests, and my reviewer approves the diff. Now I can ship it. We got a ship it button right there on the diff. When I hit that, my diff is going to return to Sandcastle. It's going to go back to the data center, although at this point we call it Landcastle, because it's trying to land the diff. So I'm going to show you a little blow-up of what's going on inside Landcastle. The key difference here is that we're going to run, again, a bunch of different builds, a bunch of different tests, but if and only if my diff passes all of those tests, Landcastle will actually push my diff to the source control repo. So now if one of my coworkers goes and pulls down trunk, they will get my diff. Landcastle is incredibly important to the culture at Facebook. This is how we keep master clean. This is how we allow our developers to iterate very quickly without having to worry about breakage in trunk. It is not OK at Facebook to land a diff without using Landcastle. So let's say my diff passed Landcastle. It's in master now. As soon as it lands in master, we're going to run tests on it again. These are called post-commit hook builds. And the key advantage here is that as a developer, I am no longer waiting on my diff. It's in master. My coworkers can pull it down. They can build on top of it. And so we can run a much more extensive set of tests at this point. If one of those tests fails, then a task is created for me, the author of the diff. And those tasks can be push blocking, so that it's impossible for the code to actually go out to users until the test starts passing again. So after my diff has been in master for a while, a branch cut will occur that includes my diff. And now my diff is part of the release candidate. We can add new diffs onto the release candidate. These are called cherry picks, individual diffs that we patch onto the release candidate to fix bugs and things like that. And every time we add one of these, we are again going to run tests on it to make sure nothing breaks. So all of these tests that I've talked about so far are per diff, per change to the code base. We have a lot of those at Facebook. So in addition to all of these tests, we have continuous runs. These happen every 5 minutes, every 15 minutes, depending on the type of test. And the key advantage here is that they don't have to scale with the number of diffs that our developers create. And trust me, our developers create a lot. So we can run a much more extensive set of tests, and we can use these to fill in the gaps. So any tests that may have been missed on diffs because they were too slow or too flaky will get run in these continuous runs. Now, because there's a whole set of diffs that may have gone in between one continuous run and the next, we have an automated bisect that goes in and finds the diff that's actually responsible for the failure so that we can generate a task for the author of that diff. We do these continuous runs on both master and the release candidate, and we also have extensive dogfooding on both master and the release candidate. So now, my diff is going to go through one last set of tests in Sandcastle before it finally finds its way into production and onto your phone. This whole process for mobile takes about 1 to 2 weeks. So to give you a feel for scale here, Sandcastle processes over 1,000 test results every second on a typical workday. And Sandcastle does more than 5 years' worth of machine work every single day. So to operate at this scale, we obviously need a lot of machines, and you can see where we started. Back in 2012, this was our rack of Mac Minis. Many of you all probably have racks that look quite similar to this. Well, at Facebook, we've come a long way since then. This is what our racks of Mac Minis look like today. And the Sandcastle tier in general includes thousands of machines in 5 data centers. So to operate at this scale, we've had to make some changes to our architecture. We started out using BuildBot. BuildBot is an open source continuous integration system. Many of you all probably heard of it. Some of you may use it. And BuildBot served us really well for about 3 years. But after 3 years, we started to hit the scaling limits of the single-threaded, single-master model that BuildBot uses, which you can see illustrated on the left here. In particular, we got to a point where we had jobs waiting in the queue, but the master could not push work to the workers fast enough to keep the workers busy. So we had both jobs waiting in the queue and workers sitting idle. You don't ever want that to happen. So this is when we moved over to Sandcastle. The key advantage with Sandcastle is that we have a distributed queue. It's built on a distributed queue. So when workers are ready to execute work, they can just pull a job from the distributed queue. So this solved the single master problem. And it also gave us an added benefit of fault tolerance. So if an entire data center goes down, we can still keep processing our developers' builds. Now, this problem is definitely not unique to Facebook. As your continuous integration systems grow, you will eventually hit these limits as well. And this solution is also not unique to Sandcastle. Open source continuous integration systems like BuildBot are also headed in this direction, so look out for those changes. Now, processing this many tests every day, failures become inevitable. And as I said at the very beginning of the talk, high signal feedback is critical. Flaky failures erode developers' confidence in our system, and we cannot have that. We need our developers to trust Sandcastle. So one of the key things that we've done to keep the signal high is we've been extremely careful to separate infrastructure failures from user failures. So a user failure means the developer did bad. The developer has a bad diff, and they need to fix it. An infrastructure failure means the diff is fine, but something, for example, was wrong with the machine that ran the diff. So we've been extremely careful that infrastructure failures get retried, and the report of the infrastructure failure always goes to us, the Sandcastle developers, and never to the author of the diff. In addition, we have an entire system of bots that we use to help keep flaky tests out of developers' workflows. These bots stress run tests in all of our different data centers, and they run the tests many times in parallel with themselves. You'd be surprised how many tests cannot run in parallel with themselves. And these bots know how to look at vast swarms of test runs and pick out the ones that have a history of flaky behavior. We run these bots before tests are ever allowed to run on diffs, And they also go and look at tests that have been in master for a while and pick out those that have become flaky over time. Finally, we have a not my fault button, so the developers can let us know explicitly if the signal that we are providing them needs to be better. So this is how we provide high signal, rapid, and frequent feedback to developers while operating at Facebook scale. Because developer efficiency is incredibly important to us at Facebook. We do not want our developers to be waiting on computers. We want computers to be waiting on our developers to produce more. Whatever the scale of your engineering organization, developer efficiency is the key thing that your infrastructure teams should be striving for. And this is why at Facebook, we have some of our top engineers working on developer infrastructure. So thank you all very much for your time. We hope you've enjoyed the conference.
Thank you very much, Katie, Christian, and Brian. I've had my brain blown, and I work at Facebook, so thank you very much. I hope you all enjoyed our sessions this afternoon. It's always our privilege to talk about the engineering work that we do at Facebook. We hope you've enjoyed the afternoon. We hope you've enjoyed the day. We hope you've enjoyed the whole conference. And we will see you back here next year. Thank you very much.